Hey everyone, today we're gonna talk about a locally weighted linear regression. I personally don't like this kind of model, but it's still a linear regression, so we're gonna talk about this in the second module. It's a bit different from just fitting a straight line into all of the data, but I've seen one guy winning a national data science Olympiad with such a model, so we're gonna touch it for a bit, and there is an important concept that's involved in this algorithm, and we're gonna do some interesting stuff with possibilities and Gaussian distribution in next lessons, but and it's related to this type of model, but overall it's just an ordinary linear regression that has a certain weight, a certain number, or which shows the importance of a certain points of all points, but this number is different for different points. It affects only the loss function, because the prediction thing when we just multiply x by theta is the same always, just like in the linear regression itself. But the only difference is the loss function. As you may see, there is a mean squared error, so just sum of the squared things, but we don't care about 1 divided by n, so to be honest, it's not literally a mean squared error, but it looks just the same, to be honest. And there is this function called something like the function of weight or something like that, but just what you need to understand is that the meaning of it and how it works. And we just have, for example, if the object is not important for our data, it just gives 0, so our error doesn't change. But when it's huge, the maximum value is 1, so it affects the error. So how it works? Firstly, we're gonna say a bit about how generally this thing works. So the core principle is that we fit our linear regression only when we give it a certain let's say parameters, a certain x that we want to predict from. So let's say this is our x input and it's a number between, say, -3 and +3. Let's say we have 1. So we see that our x is 1. And what we do? We consider only the points that lie near our x. So in this type of thing, we say x equals 1. So this third thing, we only consider those points and fit a straight line into them, because those points and those points have less weight than the points that are those points whose axes are near our x that we have given to it. And so we'd say that the core principle is that we take a certain part of data and fit a straight line into that. How this thing looks in real life, so it's just an exponential function with some negative thing and a parameter for determining which how large this certain data should be. So like whether it should be this 3 thing or it should be 2, 3, and 4, so a bigger picture. And why is this function literally taken? Because I think everybody knows everything about linear regression, how to fit it, and in most cases it's fit, this certain kind of model is fit with with least squares method too, and in a few lessons we're gonna do that by ourselves in handy. But right now, let's just take a look about how this certain thing works, because I think it's the most important one. Firstly, it's an exponential function, as you may see. So I've just taken the Desmos and printed an exponential function. And let's say we pick an x, and we go through all of the values. Let's say x equals 1, and we have a bunch of points that are actually close to 1. And in this thing, we would get 1 minus 1. So this is exponent powered by 0, and exponent powered by 0, as you may see, is 1. So we take the full error of those points. Or let's say we take x that is like, let's say 1000, for example. So we would get 1 minus 1000 or negative 999, and it's squared, so we would get an exponent powered by a huge number. And what it would get, because it's negative, it would be this way, it would go this way, and it would be really close to 0, so we don't care about it because this point is too far. So you may now understand that we take only the points that are close. And so here comes the t argument. It's the argument to control how much data we're taking, because if it's higher than the important data, then the importance for some points that were previously too far, it becomes not too far. Or on the other hand, when t is very low, the points that we consider far are now points that were previously not far. So that, I think, is everything that I want to know to understand for locally weighted linear regression. In the next lesson, I think we are probably gonna dive straight deep into the least squares method, because I think everybody just understands how would Batch gradient descent and the stochastic one work with the loss function, because those are universal things that work for every cost function, so we just don't care about them. Again, you understand, take a partial derivative from all of the data or from a certain random object and then adjust it. So we're gonna touch some interesting things. Firstly, least squares method, and then we're gonna talk about some statistics, some distributions, because if you know something about calculus or statistics, you may see that it's a part of Gaussian distribution, and we're gonna work why it works like that. So thanks everybody for watching.